Convergence. So first of all, what is sequence? A sequence in a metric space X3 is a function x from a set of natural numbers n to x, and we write the sequence x as xn. It means xn is the value of x at n. So it is a function from a set of natural numbers to any set x, and we write this as xn, where xn is value of x at n. Now subsequence. If we are given a sequence xn in a metric space x3, a subsequence is a restriction of xn to infinite subset S of the set of natural number, and if we exhibit S as n1 less than n2 less than n3 less than dash 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 less than nk less than dash dash dash, because this is an infinite set, then we write the subsequence x n k. Here k is again in the suffix of n, and nk is greater than or equal to k for all k. Because n1 is greater than or equal to 1, because n1 is a natural number, so it starts from 1, and n2 is greater than n1, it means n2 is greater than or equal to 2. And if we apply induction to this, we can write nk is greater than or equal to k, because if we assume nk plus 1 greater than nk, and nk is greater than or equal to k from here, so it means nk plus 1 is greater than or equal to k plus 1. This is by principle of mathematical induction. Now what is a convergent sequence? A sequence xn converges to x. The point x belongs to the set x if for given epsilon greater than 0 there exists a natural number n such that for all n greater than or equal to n we can find a open ball centered at x and radius epsilon such that xn belongs to this ball. See, this is the ball centered at x and radius epsilon. X is the center and epsilon is the radius, and this point xn belongs to this ball, and this xn lies inside this ball for all n greater than or equal to n. And we can also write the definition of convergent sequence as the sequence xn is convergent if for all n greater than or equal to n distance of x from xn is less than epsilon, or distance of xn from x is less than epsilon. This is by the definition of ball also. Xn belongs to this ball means distance of xn from x is less than epsilon. And this point x is called the limit of the sequence, and we denote it by writing x equal to limit xn as n tends to infinity. Also we write it like this: xn tends to x. So this is a diagram which we have for the convergence of a sequence. Now limit point. Suppose x3 is a metric space and A is a subset of x. A point x belonging to x is a limit point of A if and only if for every r greater than 0 we have a ball centered at x and radius r whose intersection with the set A, which is subset of A, is non-empty, is not equal to phi. So see, this is the ball which is centered at x and its intersection with A is not equal to phi. And we denote the limit point of set A by writing lim and within bracket A. So it means limit point of A is equal to set of all the points x belonging to x for every r greater than 0, the set which is the intersection of ball and the set is not equal to phi. And this the set of limit point is the smallest closed set containing A, and it is usually called the closure of A. And the standard notation for this is like this: limit of A or A bar. The closure of A bar of A in X is the smallest closed set containing A. So we can write A bar equal to X belonging to X, such that for every R belonging to R, this set is not equal to phi. Now cluster point. X is a cluster point of a set A if for each R greater than 0, this intersection contains a point other than X. And this is the ball centered at X and radius R, and this is the set A, which is a subset of X. So if this intersection contains a point other than X, then X is called the cluster point of A. We also call it as accumulation point. Now the deleted neighborhood. If we write the open ball B dash centered at X and radius R to be BXR minus singleton set X, then this ball is called the deleted neighborhood of X, because this does not contain this. Thus X is a cluster point of A if every deleted neighborhood of X contains a point of A. Now a subset A of a metric space Xt is closed if A contains all its limit points. So we suppose that A is closed and X is a limit point of A. Now if X belongs to A, then there is nothing to prove. Means A contains all its limit point. So we assume X does not belong to A. If X does not belong to A, then the set U, which is complement of A, means X minus A, is open. Because A is given to be closed, it means its complement is open. And X belongs to U. X does not belong to A, but X belongs to U. Therefore, there exists R greater than 0 such that the open ball centered at X and radius R is a subset of U. It means the intersection of this ball and the set A is empty set. But this contradicts the assumption that X is a limit point of A, because this is the definition of limit point of A. According to the definition of limit point of A, the intersection of this ball with set A should not be empty. But here we have seen that this is empty. Therefore, we conclude that the statement X does not belong to A is false, because we have assumed X does not belong to A. So this is false according to this contradiction. It means X belongs to A. So we can say any limit point of A lies in A. Now it's converse. Actually here it is if and only if. Here it is if and only if. Now converse. If A contains all its limit point, then we want to show that A is closed. A is closed means its complement is open. So if we consider U equal to X minus A, then we need to prove that U is open. Because A is closed is equivalent to proving that U is open, because U is complement of A. If U is not open, it means there exists X belonging to U such that for every R greater than 0, the ball centered at X and radius R is not contained in U. If it is not open, it means for every R greater than 0, there exists a point in the complement of U. Or we can say X is such that for every R greater than 0, the set which is intersection of the ball and A is not equal to phi. It means X is a limit point of A by the definition, by this definition of limit point, and it is not in A because x belongs to U. But this contradicts the hypothesis that A contains all its limit point. Hence we conclude that U is open, it means A is closed because U is complement of A. Now the Cauchy sequence. A sequence xn in a metric space is called a Cauchy sequence if for any epsilon greater than 0 we can find a natural number n such that whenever m and n are greater than n, we have the distance between xm and xn is less than epsilon. If this condition holds, then we say that xn is a Cauchy sequence, means distance between any two of its term is less than epsilon. Now we have one result. A Cauchy sequence in a metric space xt is convergent if it has convergent subsequence. Let Cauchy sequence xn be convergent in metric space. Let xn converges to x and let xn k, here k is in the suffix of n, be a subsequence of xn. It means n1 is less than n2 is less than dash 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 by definition of subsequence. Suppose we assume yk to be equal to x and k. K is in the suffix of n, and we show that this yk converges to x, means this subsequence converges to x. Suppose for epsilon greater than 0 there exists a natural number n such that n is greater than or equal to n, implies distance between xn and x is less than epsilon because we are given xn converges to x. Since nk is increasing, means n1 is less than n2 is less than n3 and so on, we have nk is greater than or equal to n. So it means following this, distance of yk from x is less than epsilon. So it means yk tends to x. Now the converse part. Let xn be a Cauchy sequence in x. Assume that x and k is a convergent subsequence converging to x belonging to x. Now we claim that the sequence xn converges to x. Suppose epsilon greater than 0 be given. Choose n1 to be natural number such that distance of xm from xn is less than epsilon by 2 for all mn greater than or equal to nn. Because we are given that xn is a Cauchy sequence, so this condition holds. Also choose k1 to be natural number such that k is greater than k1, then distance of x and k from x is less than epsilon by 2 because x and k is a convergent subsequence converging to x. So this is by definition of convergence. We observe that nk is greater than or equal to k because we have proved it in first slide also. 1 is less than n1 is less than n2 implies n2 is greater than or equal to 2, and by induction we see that nk is greater than or equal to k. If you take n to be maximum of this n1 and k1, it means n is greater than or equal to n, and we have distance of xn from x is less than or equal to distance of xn from x and k plus distance of x and k from x. This is by triangle inequality by definition of a metric. But this is less than epsilon by 2, this is also less than epsilon by 2, so it means this is less than epsilon. So where we have chosen as k, chosen a k such that k is greater than or equal to n. So it means distance of xn from x is less than epsilon, and it means xn converges to x. Now the definition of completeness. A metric space xt is said to be complete if every Cauchy sequence in X converges to an element in X. From this definition, we see that the closed interval 0, 1 and semi-closed interval 0 to infinity with metric from R is complete. But the open interval 0, 1 and 0 infinity with metric from R are not complete, because a sequence in the interval that tends to 0 is Cauchy but does not converge in this interval. Let's see by example. Suppose we consider a sequence xn and define it by xn equal to 1 upon n. Clearly we can verify that this is a Cauchy sequence in the open interval 0 to 1, because distance between two of its points is less than epsilon. This we can verify by the definition of Cauchy sequence. So we have assumed the absolute value metric induced from that on R in this example. But this sequence, this is a Cauchy sequence, but this is not convergent in 0 to 1, because we see that as n tends to infinity, 1 upon n tends to 0. But 0 does not belong to this interval, because this is an open interval. So this sequence 1 upon n is not convergent in 0 to 1. Hence we conclude that 0, 1 is not complete with respect to this metric. Similarly, we can show that 0 to infinity is not complete with respect to this absolute value metric induced from that on R. So a metric space Xt is said to be complete if every Cauchy sequence in X converges to an element in X. In this case, it holds, means these are complete, but these open intervals are not complete. And completeness also depends on the underlying metric also. Now bounded sets. We define a set A to be bounded in metric space Xt if there exists X naught belonging to X and R greater than 0, such that A is a subset of open ball centered at X naught and radius R. This is the set A, and this is contained in ball centered at X naught and radius R. So this is a bounded set. Let A be a non-empty subset of a metric space Xt. Then the diameter of A is defined as supremum of distances between X and Y, where X and Y are elements of A in the extended real number system. So diameter of A means supremum of all the points, supremum of all the distances between the points X and Y, where X and Y are elements of the set A. A subset A is said to be bounded if it is either empty or its diameter is finite. This is by using this definition. Now what are dense sets? We say a subset D of X of a metric space is dense in X if for given X belonging to X and R greater than 0, we have an open ball centered at X and radius R whose intersection with D is not equal to phi. Or we can say that any non-empty set in X must contain a point of D. If any non-empty set in X contains a point of D, then we say that D is dense in X. Let Xt boundary of a set. Let Xt be a metric space and A is a subset of X. A point X belonging to X is said to be a boundary point of A in X if every open set that contains X intersect both A and its complement non-trivially. It means the boundary of A in X is the set of boundary points of A in X, and we denote the boundary point like this. So boundary points of semi-closed interval AB are A and B. If X is equal to R and A is semi-closed interval 0 to 1, then this should not be there. Then delta A means boundary of A is the set 0 to 1. Now one more result. If xt is a metric space and S0 is a limit point of S which is subset of X, then show that there exists a sequence Xn of S all distinct from S0 which converges to S0. Let's see. We are given that S0 is a limit point of S which is a subset of X. This is given to us. Now we have to show that there exists a sequence Xn of points of S distinct from S0 which converges to S0. Because S0 is a limit point of S, therefore for each n belonging to n, there exists a sequence Sn belonging to open ball centered at S0 and radius 1 upon n intersection S minus S0. Here we have used the definition of limit point but with different notations. Now from this construction which we have done like this, it is clear that Sn is not equal to S0, because here we have written S minus S0 means complement of S0, but Sn belongs to S. So since Sn belongs to S0 upon 1 upon n, because it belongs to the intersection, it means distance of Sn from S0 is less than 1 upon n for all n. So this implies that by definition of convergence that Sn converges to S. Hence this result. Now one more result. If the range set of a convergence sequence in a metric space consists of infinitely many points, then the limit of a sequence is an accumulation point of the range set of the sequence. Let xt be a metric space and xn be a convergent sequence in X with limit point X. This is given to us. Now we have to show if the range set of convergent sequence in a metric space has infinitely many points, then the limit of the sequence is an accumulation point of the range set of the sequence. Actually, what is the sequence? Sequence is a function that assigns to each n some point xn belonging to X. This is the definition of a sequence. So the set of point is A. We may call it as range set. It is xn, which is value of x at n for all natural number n, and this is a different object. We assume that X is not an accumulation point of this range set A of the sequence. It means there is a neighborhood Px epsilon, which is a ball centered at x and radius epsilon of x, such that intersection of this ball with A is either singleton set X or phi. If we apply the definition of convergent sequence for this epsilon, we get some natural number n such that for all n belonging to n, we have xn belonging to this ball. This is by definition of convergence. It means for all such points are in A. A is this set. So for all those n belonging to n, xn is equal to x, because this xn converges to x. So the sequence is a trivial convergent sequence. All its tail consists of values of x. So A can be at most x1, x2, xn and x. And A is finite because it is from 1 to n only and consists of limit point. So it is finite set. So a finite set actually never has a accumulation point in a metric space. So X is not a accumulation point if and only if A is finite. So the theorem is proved if the range set of convergence sequence in a metric space consists of infinitely many points. In that case, limit of the sequence is an accumulation point of the range set. But X is not the accumulation point if and only if A is finite. Thank you.